So today is another really exciting and big topic. So we're going to go over pre-training. So pre-training has really become a key part of most advanced NLP systems. It's kind of this initial, as we'll see, this kind of initial stage that you do, and it allows the model to become more data efficient to pick up a variety of capabilities. And it's really become an important part of um, NLP. So a lot of this is kind of evolving each year. So here, parts of it will be from, a few years ago. Some of it will be from, within a year, within 2 years. So it's very much an evolving field. Um, so already we're at lecture, what, 6, and we're already starting to look at some very recent techniques. So to recap, so far in this course, we've talked about a variety of things. So we've talked about classification. We talked about the task of language modeling. And then we went into these various architectures like recurrent neural networks, simple feed-forward neural networks, as well as transformers in the last lecture. And so far, I've been showing you these kind of toy tasks like generating names. One of them was like reversing a name, things like that. And in all of those different examples, we were training the model from scratch, even to like classify, whether a movie review was positive or negative. And we were training it from scratch, meaning we set the weights to just random numbers, and then we run the PyTorch code and we get some model. And this model is very specific to this one task as well. Like if we train the model to generate names, then it's not going to be able to say whether a movie review is positive or negative, for instance, and vice versa. So this was actually the paradigm for a long time in NLP. And now we've kind of in a different paradigm, and it's based on pre-training. So here we'll first pre-train a single model, and you can kind of spend a lot of computation and resources to pre-train this model. And then the benefit is that you could then adapt the model to many different tasks at a kind of lower computational cost. So the basic idea, just before going into details, it's good to see just a high-level picture. We're going to collect a bunch of data, as much data as we can, and then we're going to run this pre-training algorithm, and we'll go into the details. And then we'll get some model as a result of running the algorithm. And this goes by various names. Some people call them foundation models. I think I'll use the word base model. And so you get this model. And the model could be a language model. We'll see one other example of something else called a masked language model. But in general, you get some type of model from pre-training. And then you try to adapt the model to different tasks. So it could be sentiment analysis, translation, following instructions, kind of a general task, solving problems, things like that. So for adaptation, we'll have at least two different lectures. We'll have several lectures on how you take a pre-trained model and adapt it to different tasks. Let me just go over two that we'll cover in the next two lectures. So the first is prompting. So here we take the model and we don't run any additional learning algorithm on it. Like we don't update its weights at all. We just, in its input context, kind of describe a task, maybe give some examples of the task, and then we try to have the model perform the task. So a few years ago, this would have sounded absolutely crazy. Like, why, why would this work? But it turns out to work with these language models that have been pre-trained for a while. And this idea of kind of describing a task to a model without training it further is now kind of, somewhat standard. And it's what you might do, let's say if you're using, I don't know, ChatGPT, then you kind of describe what you want it to do. Maybe you give it some input output examples, or maybe you just kind of tell it what to do, and then it can perform a task. So we'll go into this in the next lecture. We'll talk about the pros and cons, but this is a perfectly viable way to try to get your model to perform various tasks. The other is called fine tuning. So here the difference is, well, first of all, we have some task data. So we have these input and output pairs. Um, and then we'll fine tune the model, which is to say we will actually run some optimization algorithm, which is updating the model's weights. Um, so here the difference is that now the model's weights are somewhat specialized maybe for this task. Like you could fine tune the model for translation. But then the trick is that you can kind of fine tune it for a very general purpose task and still perform a lot of different tasks with the model. So we'll talk about this in lecture 8, but these are called instruction following models, where the model is fine-tuned kind of for the task of performing different tasks. It's kind of a clever trick. So anyways, today we're going to focus on this first step, which is called pre-training. And there's a question of like, why would you want to do this pre-training? Um, well, first is this idea of transfer learning, which is a kind of classic idea in machine learning. We're not going to go too in depth here, but here the basic idea is you are taking some knowledge from one task and then applying it to another task. And so here we want to do some kind of pre-training task, and we'll talk about what those are. And then the idea is, maybe this model has learned something which can then be transferred or applied to another task. So what does that actually mean? Well, it could mean that now when you go to perform a new task, say like translation, now you might actually need less data to reach a given level of performance. Whereas if we want to train a model from scratch, say for translation, then you might have to assemble this huge training data set um, in order to train the model specifically for translation. Another thing is you might just get um, better task performance. So slightly different. It's not saying, you need less data to reach the same level of performance. Sometimes it might just not be possible to beat using a pre-trained model and then say fine-tuning it um, with the amount of data you have. So you might not have enough data to reach this level of performance. And then this also is just convenient for many reasons. So first, you can think of this pre-training phase as some kind of expensive use of resources. But then in some sense, it's covering the cost then of developing a new model because it might be more computationally efficient than to, adapt the model to a given task. And this is certainly the kind of paradigm we're in now, where, as we'll see in today's lecture, sometimes a large company will pre-train a model and then people can use it in various different ways. So when we think about pre-training, I showed the kind of high-level picture, but what are some of the major factors that come into play? And again, this is still at a kind of high level. We'll go into the technical details. So you might see these different pre-trained models like BERT, Llama, DeepSeek, and the names are kind of all over the place. But then you can really kind of uh, um, identify these by kind of four major factors. The first is the architecture that the model is using. Typically nowadays they're based on different versions of variants of transformers. But as we saw at the end of the last lecture, if you look at specifically which transformer is being used, people are kind of modifying them in different ways. Second is the task. So what the model has been trained to do during pre-training. A big one is the data that is used to do the pre-training. We'll talk about this later. Um, and then actually it turns out to be very important to choose the hyperparameters well. So to choose the learning rate well, to choose even like the batch size well. And we'll actually go into this really in depth later in the course when we talk about how you actually scale up the model um, to do this pre-training. So it will require a lot of computational resources. So you'll basically have access to a bunch of, GPUs. And then the problem becomes like, how do you kind of optimally make use of those GPUs? And changing the hyperparameters can actually have a big impact on that. Um, so today we'll go into two different tasks. Um, so one nowadays is still used, called mass language modeling. It was really popular, I don't know, something like 5 years ago. And then we'll go into using this language modeling objective that we've talked about for doing pre-training. Then I'll give an outline of things you're concerned about with data, so sources, quality, and quantity. And we'll actually look at a couple real examples. Um, and then at the end, as long as we can get to it, I'll talk about some useful ideas for, I guess I'm calling it thinking about pre-training. So thinking about this as a process where we have a lot of compute and we want to think about like, how do we allocate it towards training a bigger model or training on more tokens? And there's been some kind of systematic ways of thinking about this, which are called scaling laws. Okay, so first we'll go to the two different tasks. So we'll start with masked language modeling. So masked language modeling is maybe like it sounds. So the task is we have some input sequence. You know, this could be it could be anything, you know, a web page, a sentence, whatever. And then what you're going to do is you're going to mask out some tokens. And the task is essentially to predict the masked tokens. Okay, so like if this was I don't know, uh, you know, the president of the United States is, and the name happened to be masked out, or even like the president happened to be masked out, then you can kind of see that the model is kind of forced to predict something and over the course of training, kind of store useful things or useful representations in its parameters. So that's the kind of intuition. And if we look at maybe like it written down a bit more formally, so here again we have our pre-training data set and you have your model parameters. And then this is basically saying like, okay, for each sequence X in the pre-training data set, and then here we have this expectation. So this is basically saying that somehow we're going to have some function that corrupts or masks out the sequence. And then you're going to apply this loss function. And what it's saying is, okay, you go over each token that has been masked out, and you are just maximizing the probability of the masked out token, like the actual version of the masked out token, given this masked sequence. Okay, so it's kind of similar to the loss you see in the next token prediction, but now instead the model is seeing this masked thing and has to predict the masked word. Okay, so in a bit I'll show an example of how, like very concretely, you might do this masking, so this corrupt function. But we can think about this in two different ways. So yeah, I guess I'm not going to go into too much detail here, but there's this kind of classic uh, series of methods which are called denoisers or denoising. And the task is basically to go from some corrupted input to a uncorrupted one. So basically like reconstruct the input or kind of remove the noise from the input. And so you can think of this as being one of these kinds of methods where we have this input sequence and then we're adding some noise to it with these masking tokens. And then the model's task is to kind of denoise it or uncorrupt the sequence. And then it turns out that, you know, I've talked about this idea of maximizing likelihood. It turns out that this masked language modeling objective is a bit different. So again, I won't go into too much detail here, like showing the equations and everything. But it turns out that when you provide this masked input, when you have these different conditionals, which are like masked input and then some unmasked input, then you can't always have this kind of neat chain rule decomposition that you get with the autoregressive model. And so it doesn't necessarily, when you're summing over all of these, it doesn't necessarily correspond to this joint distribution over the whole sequence. And so this goes by the name of pseudo likelihood. And you can kind of see that it looks somewhat like maximum likelihood, but then it's not exactly the same thing. So anyways, that's the kind of background for it. And um, now we can look at an example, then maybe I'll pause for questions. So here's an example, and this was a really famous model called BERT, and it's from 2018. And so here the architecture was a transformer, and the data they were using was based on different books. So they had this books corpus, and then English Wikipedia. Okay, so that'll be the D in the formula on the previous slide. And then from this data, you get these like different sequences. And they do mass language modeling. So here they formatted the data like in a specific way. So they were looking at like two uh, sentences or like spans next to each other. So you could see here they have this special token, which like denotes the start. And then they have these two special separator tokens. Um, and yeah, had the data of this form. I don't remember exactly why they do two sequences. I think like at the time, a lot of tasks involved a kind of input and output and could kind of be neatly decomposed in this way, like translation with just like single sentence translation. There was other tasks called like natural language inference where people would want to say like, okay, is this sentence contradicting this one? And a lot of the benchmarks were based on that. Um, so potentially why that's why it's kind of split up like this. Um, so then if we look at their actual kind of corruption function or masking function, um, so here you don't have to actually worry about the like why they specifically did this because people found in the future that you could do other things and it still works. So there's a follow-up called Roberta, which actually got better performance. And it actually has a simpler masking procedure. But I'm just trying to give you some sense of, what's actually done here. So here, 80% of the time, they'll substitute their input token with mask. And then 10% of the time, they'll substitute the input token with a random token. And then 10% time is no change. Um, so basically, if there's a mask here, then the model has to predict the missing, token. It also has to kind of pay attention to whether these tokens are real or fake. So that's what this random token is. So if there's some, unusual token here, then the model will learn to predict the true one. Um, so 80%. And then I think of like these, you determine like what percent will be modified, and then 80% of those will be masked, 10% will be random, and 10% will be no change. Um, so that's the basic idea. So actually, does anyone remember, can anyone predict the mask tokens here? Okay. Okay, let's see. Yep, perfect. Okay, so we have a distributed mass language model um, in here. So, oops, let's see what I have. What else? So yeah, any questions on this or um, on this BERT model? Mhm. Yeah, so I need to check on the exact percentage, but I think here, um, yeah, let me check after this. So one option is you apply this and it's on 80% of the sequence. It does sound like a lot. Another is you say like, okay, 20% of the tokens will be corrupted. And that's what I think it is. And then, okay, of that 20%, 80% will be masked, 10% will be replaced, 10% will be um, just left the same. And then only on that 20% are you applying the loss function. Yeah. Okay. And it turns out in this BERT, they actually had additional losses. So they had they had ones based on the two sentences, but then like this next sentence prediction was found to not be needed in Roberta and things like that. So this was a huge, research area to figure out what was the best way to train a mass language model. And this was the kind of first one that was done at scale. So then if you think about, actually, yeah, maybe before moving, can anyone think of a downside of having this as your pre-training task? Mhm.
uh, predicting a if you mask a phrase, that's harder to predict than masking just tokens. So you want to train your model to be able to predict entire phrases instead of just tokens.
Mm. So potentially just randomly masking some tokens, it could be better to mask like consecutive spans and things like that. Yeah. So people actually did look into that, like changing the strategy used to mask. So that's definitely a downside of or that's a potential downside of this BERT. Um, but I'm actually looking for something slightly different. Mhm.
So generating new tasks without having the future token value might be difficult because here you're accessing not just the past token but also the future token. But when you're trying to generate something, you don't really have a future token. So trying to generate some new sentences
Yeah,
could be troublesome with this.
exactly, exactly. So this pre-training task turns out to be good for kind of learning representations and then fine-tuning, which I'll show in the next slide. But it doesn't turn out to be as effective for generation tasks. So you would still need to train another kind of generator, on top of this model. And again, yeah, the model's learning to, potentially depend on these future tokens, and there's not really a consistent algorithm for generating. Like, left to right is a kind of consistent strategy. So you can try to generate with these, and there's been like papers about that. Um, but it kind of turned out to not be, um, yeah, as effective for the generative tasks. So the typical way you would use these is you do some fine tuning and you introduce these additional weights. So here, this is basically what we've seen in other lectures where you have this output layer. So here we're just attaching an output layer to, it could just be one of these output vectors. Um, Actually, what they do is typically use this like special token and then just put the output layer there. Um, so yeah, and then you could have your model, predict do classification, for instance. And then we'll talk about fine tuning in the lecture, but it's basically, running uh oops um it's doing this like sequence to sequence training that we actually saw last time with some data set. So here you might have movie reviews and then these three scores are positive, neutral, and negative. And now you can fine tune and um have a model that can perform the movie review classification. Um So this is really the common way to use these. Um, and this kind of paradigm somewhat like revolutionized NLP, in 2018. Because now instead of training this movie reviewer from scratch, now we can kind of leverage all of the different things that the model has we can leverage the representations that it learned during this large scale pre-training for doing the various tasks. Okay, so any questions about this? Yeah, so this just means, so if you remember like in the previous lecture, we were talking about the sequence to sequence models, then you assemble this data set and it'll have an input sequence X and an output sequence Y. And then we'll basically apply the cross entropy loss to, oh, well, here it's not a sequence, here it's just a label. So now you just do this classification loss on the label, and that's the cross entropy loss from lecture number 2. Yeah. Okay.
What's the difference between having a mask token on the input layer or applying just dropout in the input layer?
Dropout on the input layer. Well, I guess dropout, so dropout will, so I guess typically you'll apply dropout to a layer, so you could apply it to the embedding layer, maybe you're suggesting? Yeah. And maybe one difference is like dropout is usually like per dimension. So you're masking out some dimensions of the embedding. Whereas maybe the masking is more extreme because it's literally changing it to this new token embedding. Yeah. Yeah, this is another thing. I don't know if it's necessary. I guess the intuition would be so when you have a mask token, the model is forced to do some prediction task. The random token is a kind of prediction task that requires reasoning about the input in the sense that like it has to identify that this token is kind of out of place. So maybe it's a slightly different task than just predicting a token when you know that it's masked out. Okay. Sounds good. So yeah, I just wanted to say, so these are still very useful. So now, the trend is to use language models, but these can be very useful, especially for classification tasks. So it's still, very popular to train a classifier with one of these mass language models. And there'll be like, standard like notebooks or libraries for training this. So it could be very useful in practice if you need to like, train a classifier or fine-tune a classifier. Okay, so then now we'll go to autoregressive language modeling. And so here, this is doing what we talked about in lecture 3. So here we want to take in some context, so some previous tokens, and then basically predict the next token. And then with the autoregressive language model, if you do this kind of for each context and each next token, then this is equivalent to using this chain rule to kind of break down the probability of the or to break down the joint distribution over the full sequence into these individual next token distributions. But anyways, like when you compare it to mass language modeling, you could see it's a bit different. It's only given this history and you're just predicting this next token. So then this is like the same loss that we've seen before. So does anyone know why it's written MLE? It doesn't mean masked language estimator.
Maximum likelihood estimate.
Yeah, exactly. So this is kind of doing this maximum likelihood estimation. And it turns out to, for the autoregressive model, be of this form. And this is what we talked about in the previous class. It kind of reduces to the problem of, given the previous context, kind of increase the probability of the next token that is in your training data set. So again, here we have some training data set D. It'll be a bunch of different sequences. And then we're going over the data set and then saying like, okay, for each next token, predict it. And so, yeah, this maximizes likelihood. So the model's parameters are set so that the likelihood of the training data is maximized, like if you optimize this successfully. And to give two more kind of intuitions for this, first, I'm just going to review the same derivation that was in the previous lecture. So you could think about this as kind of fitting some underlying data distribution. And then this is another one, which is you can also think of this pre-training task, this language modeling pre-training, as the model actually learning to compress the data. So that's kind of interesting. So we'll have a slide on that. So here, if we think about this pre-training task in terms of fitting some distribution, then we basically are saying that like, okay, our pre-training data, we assume that it is drawn from some data distribution. So this could be like the distribution that kind of gives rise to all the data on the internet or something like that. So sometimes it's a bit mysterious, but you assume that your training data is sampled from some underlying distribution, and then now we want the model to kind of fit it. So we'll call the data distribution P star, and then we could do this like distribution fitting by minimizing this divergence between the two distributions. Okay, so then if you write out the definition of this KL divergence, then it's just this, and we've seen this slide a couple times in the other lectures. Then what you could do is you can expand this out, and you'll get this term here, and then you'll get P star log of P star right here. Does anyone know what P star log of P star is called?
The entropy of P star.
Yeah, exactly. The entropy of P star. So maybe that's a good quiz question because it's not in the slides. But anyways, I'll get back to the entropy on the next slide. There's a reason I pointed it out because it's actually interesting to think about. But anyways, so now you have this, and that is the entropy is constant with respect to the model parameters. So if we're minimizing, it's not really, we can kind of ignore it. This is just writing this as this expectation. And then we're basically saying that our data set is a sample. It's this like Monte Carlo approximation, or it's helping us form this approximation of this expectation. So based on the kind of finite number of samples in the data set. And then you could see here that, yeah, if you flip the min and negative and do max, then this is maximizing the log likelihood. Okay, so again, we're predicting the next token, but it can kind of, it's a bit more interesting than that. It also turns out to be like fitting this data distribution. So then here's another one, and this one would probably require a while to really get. So here I'm just gonna kind of just like sketch the idea of this compression. And if you find this interesting, there's a link to a paper that kind of goes into this in more detail. But I think it's kind of useful to know about. So there's this idea of compression. And so in compression, you want to compress the data from some distribution. And the way that you'll compress it is to basically try to come up with this binary representation of the data that is as short as possible. So like you might try to take in some like input sentence, and then try to represent it as like zeros and ones. And then the thing is that you have to do it over any possible data. So you have to have a really clever scheme for any possible data element, kind of coming up with a short sequence of zeros and ones, and then being able to go back to the data, so like decompress. So this thing that goes from the data to the sequence of ones and zeros is called a code. And here I'm not going to go into the details, but it turns out that there's this kind of clever algorithm called arithmetic coding. And it basically allows you to take a autoregressive distribution and turn it into a code. So here's the figure, and I purposely made it small so that I didn't start explaining all the details. But it basically comes down to like looking at so for like the first token, looking at your model's next token probabilities, and you kind of come up with this like ranked this like partitioning of between 0 and 1. And then you can do that for each next token and kind of make this like partition. And then it turns out that you can turn that into this binary sequence by doing these kind of like splits. So you split 0 and 1 in half, and you split 0 and 0.5 in half, and so on. So again, I'm purposely not going into the details, but here I'm just saying that it's possible to actually like take a language model and have it produce these codes using its next token probabilities. So then if you think about like what is the best possible code length that you could get, like what's the shortest possible like the best possible code you could create, then the expected length is equal to this entropy of the distribution P star. And so this is this like classic result from Claude Shannon in 1948. And yeah, so that's like the best you can possibly do. Now, suppose that we use a language model to do this this coding thing. Then we're not actually using P star to do the to compute the code. So we incur some loss. And that loss is called the cross entropy. So it's basically the extra code length you get as a result of using a this like imperfect model versus the target distribution. Then this cross entropy decomposes into these two different parts. So you could see cross entropy is equal to entropy and KL divergence. So then basically if we want to achieve the minimum code length, then you could see that it corresponds to minimizing this KL divergence between P star and P theta. And actually that's exactly what I just argued this next token prediction does. So I'm going through it kind of quickly, but there's this kind of really cool idea that when you're doing this pre-training, or when you're doing this next token prediction, the model is actually minimizing this divergence with the target distribution, and that actually corresponds to learning to compress the data better and better. And so why is this idea of compression useful? Well, just like at an intuitive level, you could think like, what is required to compress new data? Well, maybe you have to learn kind of good reusable representations of the data. Or if you have kind of algorithmic data, maybe the most efficient way to compress it is just to like learn the algorithm that describes the data. So yeah, one way to think about the pre-training is it's going over this like massive data set, and it has to figure out some way of kind of cleverly compressing kind of future data. So this is the paper. I think it was by authors at DeepMind. These ideas have been around, for a long time, and this connection's been known for a long time. But then this is one that kind of puts it into terms of pre-training on language models if you want to read about this more. Okay, so that's some maybe theoretical motivation for doing pre-training with the language modeling task. Now we're going to actually go into like very just concrete things and look at specifically what is involved in doing this pre-training in practice. So if we just look at this equation, then or maybe you could step back and you can say like, okay, maybe you've heard of these different language models and they're developed by companies. So companies will have these teams, you know, of people now, and their job will be to specifically maybe pre-train a language model. And you could think about like what are they doing? Like there must be so many different things you can do, right? But what we can do is we could look at the equation that's being used to pre-train the model, and then we can actually classify everything into kind of these three different categories. So one thing you could do is you could try to design a new architecture, or you could try to like increase the number of parameters in the architecture, so train a larger and larger model. And that will potentially impact the pre-training. So you might like get a lower loss. Another thing is you could see that like the input to pre-training is a data set. Right? You have to do the pre-training on some data set. So you could spend a lot of time and a lot of effort thinking about like what is the right data to pre-train on. So we'll talk about that in the next part of the lecture. And then the third thing is in order to kind of minimize this loss, you have to actually run some algorithm with different hyperparameters. Like you have to choose the learning rate, you have to choose the batch size, and you have to figure out how to run it on a lot of GPUs. And so we'll talk about those in, we'll talk about the GPU part in a later lecture. Okay, so it turns out that a lot of time and a lot of effort, especially go into this data part, because you could see that it's one of the key kind of inputs to pre-training. So first, let's just look at one example or two examples. So one of the original papers that really started to get really strong results with doing this language model pre-training, there was GPT, which was a recommended reading for this lecture. And there's GPT-2. Or maybe GPT-2 was the recommended reading. Does anyone remember? GPT-2? Yeah, so GPT-2. And so they had this transformer, and at the time it was, you know, massive, 1.5 billion parameters. And then this amount of data was just like, you know, massive as well, millions of web pages from this data set called web text. And they were able to train this model, and it was able to perform some of these tasks like, you know, sentiment analysis, other things like that, by just providing, just like giving the model a prompt. And then they're also able to fine tune it and achieve kind of good results. Now if we fast forward a bit, so to Llama. So by now there's like Llama 4, but here's the original Llama. And back then they would give the details of the data that the model was trained on. They don't do that anymore. But here you could see that the sizes of the models have gotten a lot bigger. So now the smallest one was like 6.7 billion. And the amount of data has increased by a lot. So here I don't have the number of pages, but this will be much smaller than what's here. And you could see that it's broken down into different parts. So you have this web data from Common Crawl, you have some code data, Wikipedia, archive, so on. And so now if you look at the number of tokens that the model's pre-trained on, it's in the trillions, so 1.4 trillion tokens. And then here's the actual loss that you get, that they got as they were pre-training the model. Right, so again, we're just minimizing this loss, and then we can actually plot it during pre-training. And so on the x-axis, we have the billions of tokens that have been pre-trained on, and then you see the loss. So can anyone find some interesting patterns in this plot? And they could be really obvious.
At least in terms of training loss, there seems to be like a diminishing requirements to like doubling the parameter size.
So doubling the parameter size has diminishing returns. Okay, yeah, that's good. We'll return to that one later. How about an even simpler one? So one thing is that like it looks like just training on more tokens is helping decrease the loss, and maybe some of them are leveling off, but it looks to be a fairly consistent gain. And then another thing is that although there's maybe some diminishing returns, it looks to be beneficial to just increase the size of the model and train on the exact same data. So we'll return to those two things in a bit, but maybe for now, for the next section, we're going to talk about data. And so from this, we could see that, maybe all we need to do is just get more and more data and just keep training the model longer on it, and it'll keep getting better. Oh, another thing to note is that this plot here is in terms of training loss. So we don't actually know whether this model is good for anything. Maybe it's just good at minimizing this loss, and that doesn't actually correspond to anything useful. So we also have to talk about like how you would evaluate a pre-trained model on different tasks. So yeah, one thing is to just look at the loss. So you could look at the training loss, validation loss, and test loss. You could see whether something weird is happening. So you could see like here, there's these different spikes. Yeah, maybe some issue happened there and they had to roll back the training or something like that. You can also compare models. So you could see that like the bigger models are better in this case. But if you want to actually perform tasks without modifying the model, as it's being trained, then you kind of want to rely on prompting. So this technique called few shot prompting, we'll go into more detail. We have a whole lecture on kind of prompting and in context learning. But this was popularized in the GPT-3 paper. And so the idea is, again, you basically describe the task in the input prompt. And then here it's providing 3 different examples. And then you could basically just use this trick, which is like, okay, since these models are predicting from left to right, then to test the model on a new input, you could just give the model the input, and then it's basically just following the pattern of completing the examples. Okay, so then in this way, you can have the model perform a task like translation without kind of fine-tuning it or modifying its parameters. So here's what it looks like if you do this as the model's being trained. And it's actually kind of interesting. So as the model is getting lower and lower loss, it appears to be getting better and better on most tasks. But can anyone have any like thoughts about these plots and maybe compare them to the loss plots that we saw earlier? Okay, one thing is that like if you let's look at this line for instance, then this red model is fairly similar to the green model. I mean, maybe at the end, but I'm not sure. Maybe it's noise as well. Whereas if we look at the loss plots, then the red model is pretty much consistently better than the green model. So when you evaluate on the actual tasks, sometimes you see differences with just looking at the loss. But then broadly speaking, it's kind of good that there's some correlation between the loss and the task performance. Okay, so now if we think about practical tools, so if you haven't heard of the site called Hugging Face before, then it's a good thing to know about. It's kind of a ridiculous name, but that's fine. So here they have this hub, I guess, and the hub has different models as well as different data sets. And so you can go and now, even if a large company pre-trains a model, sometimes they'll upload it to Hugging Face. And then you can actually download it using their software package. You could use other ones, but here they have this like really easy interface for loading the model. So in the code example for today's class, it just shows doing this. So here we have Hugging Face and the software package for accessing it would be called transformers. And yeah, you can go pick a model. So this one is called small LM2 360 million. And then it's loading both the tokenizer and the model. Then we can actually use the model. So here we have these different prompts, the meaning of life, some addition problem, and oh, this is actually from last semester. So I was trying to, why don't we say September 12th? So we could see if it could predict the future. And I think this is loaded in. So yeah, like this is a pretty small model. It's just running on my laptop. And it gives us some meaning of life. It gets this incorrect. And then it says it was 100 degrees on September 12th, 2025. So actually a lot interesting here, and we'll talk about these issues throughout the course. So we'll talk about what are called hallucinations, where it's fabricating fake info. We'll talk a bit about this kind of logical reasoning and how you might improve this. And then, yeah, also just general use of models for advice, I guess, and whether that's a good idea. So, so anyways, if you haven't seen this before, very useful way to use these pre-trained models. So any question about the content so far before we move to data? Okay. So yeah, we observed that more data in this plot was leading to better loss. So what are some different factors? So first, quantity, how much data you have. Quality, so you could have like infinite amount of just like random zeros and ones. So you also want high quality data that's actually beneficial. And then coverage, so you could have a lot of high quality data in one domain, say like math data, but then the model won't work well. I don't know if you ask it the meaning of life or something like that. So if we look at the general trend is over time, the data quantities that are reported for pre-training are increasing. So we went through Llama 1 in the previous slide, and now there's a kind of next order of magnitude. So models are being trained on like 15 trillion and probably even more. This was, I think I updated this at the beginning of 2025. Oh, and just as a reference point, all of Wikipedia is about 10 billion tokens. So yeah, 10 trillion is yeah, kind of a lot of data. So a large source of data is from the web, and there's different ways to get web data. You could even build like your own crawler for the web, and maybe some companies are doing this. But if you're not able to do that, then there's these different organizations that will provide these kind of snapshots of web pages. So one of the really popular ones is called Common Crawl. And what happens is if you look at the Common Crawl data, then it's just extremely kind of low quality. So first of all, it's not in kind of text form, it's in HTML, and maybe we don't want to train the model with all the HTML tags and all that. So yeah, you'll have to do this extraction phase. Then you'll have to filter the data according to different criteria. We'll go into some examples. And then it turns out that they'll do these snapshots periodically. And so you can imagine that you might want to consider multiple snapshots because there might be new data, but then there's like tons of duplicates. And so you really have to deduplicate. And when you're doing it at this incredibly large scale, it's not a matter of just like, I don't know, doing like string matching. You have to use a different algorithm to do that. So let's yeah, briefly talk about some of this. So again, for extraction going from HTML to text, you often have a lot of boilerplate in different web pages, and you might just want the kind of main content. It also turns out to be pretty tricky to retain kind of different types of mathematical content. So here's a paper that was trying to scrape mathematical data, and they found all these different ways that the math was represented. Sometimes it's like in this alt tag and things like that. And so you really have to look at the data and kind of be careful that you're yeah, doing this extraction properly. You could imagine for code, same thing happens. You might have like a tutorial about code and you have to decide what you want to do with that kind of data. And then it turns out that the decisions you make for this extraction phase can have an impact on performance. So this was the other reading for today's lecture. Here they kind of open sourced all the different ideas for processing pre-training data. And here they're showing that using their kind of custom extraction versus the default one, it actually translates to differences in the model's performance after you pre-train on the data. Then for filtering, so this is just not looking maybe at like the deep semantic content of the pages, but just like filtering out things like repetitions. A lot of the times there'll be a decision of like, okay, do we just want to train the model on English data or just like some set of languages? If not, maybe filter out the other ones. And then, you know, when you think about the entire internet, there's just kind of odd pages that come up, like empty pages or ones with like auto-generated text or like debug traces or just weird stuff. And so once you start looking at the data, you realize that you have to add in all of these different filters, and and it could be, you know, millions of pages are kind of garbage and you don't want in the pre-training data set. So here again, you can see that these decisions actually translate to impacts on the model. So here they were trying all of their different filters or this strategy from this prior work C4. And then there were, I won't go through each one, but removing some of them actually leads to drops in performance. Then for deduplication, the one typical algorithm that's used is called min hash. So again, when you're doing this at scale, it's you can't really do this exact deduplication, and then it's not even clear what it means to deduplicate. So like, does it mean duplicate pages, duplicate paragraphs, duplicate sentences? Yeah, some of those things are like decisions you have to make, like what granularity you want to deduplicate at. Then you need some algorithm which you can run kind of at scale. And so one of the fast ones is called min hash. So I probably won't go, or I won't go into the details of how that's implemented, but it's good to have seen this name before, so then you can go look it up if you have to use it or if you see it in a paper. And then there's like this different decisions will have kind of different effects. So like in this paper, they found that deduplicating individual snapshots was better than global deduplication. So over all the snapshots. So potentially when you run this algorithm over like the entire corpus, then it's just coming up with too many duplicates and you throw away too much data. And so things like this end up having, impacting performance. Let's see if that's, yeah, so here's the global in pink, and then here's their kind of best strategy. Okay. So then if you wanted some really concrete sense of pre-training data, so different organizations are, making an effort to make as much as they can publicly accessible, which is really helpful for learning exactly how things work and things like that. So especially this nonprofit AI2 is trying to do this a lot. So they have this series of data sets as well as language models that are kind of fully open. So here's an example. The data set name is called Dolma. And maybe I won't show the code. The code is just doing like a wget on the URL. But you can actually go and look at the pre-training data and see very concretely, like, okay, this is actually from Common Crawl. And you can look at the actual source if you want. So yeah, you can go explore that if you want. Or maybe there's some interesting, projects just based on like understanding what's in the pre-training data, something like that. And then there's coverage. So this is kind of saying, yeah, does the data cover the domains you care about and in the right proportions? So if we remember, we could think of pre-training as kind of fitting this data distribution. So therefore, the data distribution that you're fitting kind of matters a lot. So web data is not necessarily the same as like math data. It's not necessarily the same as like educational data. It's not necessarily the same as code data. Of course, there's some overlap, but let's say you're building a model and you really want it to be good at code, then you have to think about like, okay, is the pre-training data, does it have good coverage of code and like the languages I care about and things like that? So one common technique for doing this is based on learning a classifier and then filtering out data. So can anyone tell me like what, let's say you're trying to filter, whoa. Oh, there's one of those Pittsburgh flies, sorry, lantern flies. Anyways, let's say you're trying to learn a classifier, and here the idea is you go over every page in the pre-training corpus and then say, do I want to keep this classifier or not keep it? Then what are some kind of things you want to take into consideration for this classifier? Maybe it's too broad of a question. Well, one thing is these pre-training data sets are huge. So you can't necessarily use like a massive language model to decide whether you're going to keep a document or not. So the classifier has to be very efficient. And then you have to come up with some like examples to train the classifier of what is good data and what is bad data. So those are two things to take into consideration. So here's an example where they were trying to specifically identify math content. So they built this classifier specifically for math. And here they had this trick where they like removed LaTeX from a page and then tried to predict whether the page actually included LaTeX or not. So I guess the thought here is like the model could actually, if a page looked like it's likely to have LaTeX, then yeah, then maybe it's a more kind of mathematical or math-related page. And so from that, you can get some label again, because the hard part is coming up with a lot of good examples of like mathematical versus non-mathematical pages so that you could train the classifier. And then these classifiers are typically based on really simple ones. So actually, this idea we talked about in the first lecture, bag of words, where we just discard all the word order. The bag of words classifiers are often used for this kind of filtering. So yeah, because it has to run extremely fast. Then in practice, doing this is kind of a whole, you know, um, engineering slash research project, and there could be these multiple phases. So you could see here the math score filter is one of just like 6 different phases. And you could see that here they went from 237 billion pages to 6 million documents at the end after doing all the filtering. And then this is another one that's open, so you can go look at the data if you want, called Open Web Math.
Goes into the manual filtering that dropped it by 1.5 million still.
Manual filter. This might that's a good question. So they did describe them in the paper. I don't remember off the top of my head, but it might literally be, you know, now that we have what we consider to be our final data set, let's like let's manually inspect some documents, and maybe it was still including like um I don't know, advertisements for uh math courses or something. And that's not like the goal of their data set. Something like that, but I'm pretty sure they would have it in the paper about this. I just don't remember. Mhm.
Now you are going to, once you filter the data, are you going to train your model only on the filtered data? Like, not at
Yep.
all other.
Yeah, so that's a good question. So we'll get to that in a bit. So for these domain-specific models, they're domain-specific data sets, they're typically like grouped in with a bunch of other data sets. So you'll have a kind of general domain data, then you'll have these like more specific domains, specific ones like math, code, whatever.
We said like one of the papers like filtered out too much data. On this, it's like if you go from 237 to 6 million, that's filtering out too much data.
Yeah. So that'll be the trade-off, like having high quality data versus high quantity. And there'll be some optimal, and it's probably I don't know if there's any, you know, there's kind of engineering and maybe like science within different companies of doing that, but that's the general trade-off. Mhm.
One question, so like we talked about deduplication, but we also said like we want the data in the right proportion. So when you are sampling from a distribution, if you do deduplication, you are actually changing the distribution itself, right?
Yeah, that's true. So so yeah, if you think of it in terms of like sampling from the distribution, it is changing the distribution. In terms of duplicates specifically, what will be done is, let me see if I can, or let me just talk through it. So the way that they'll have these different data set splits is they'll basically be sampling different batches of data. And so sometimes if you have a really small data split, it'll actually be seen multiple times during training. So sometimes the model will see the data over again. And so if you deduplicate, maybe you have more understanding of exactly what the model is seeing. Whereas if there's duplicates in there, like without you knowing, then maybe it's harder to reason about.
First, thanks. Maybe we want the model to have generate that kind of document often. So
Mhm.
deduplication is inherently changing our data.
Yeah. Yeah, I mean, all of these things are, so there's also been some work showing that you know, deduplication isn't like within some setting, deduplication is not as harmful as previously thought and things like that. So all of these things I would just view as different like concepts. And then if you're going to build and pre-train a language model, you have to consider all these things like, are we doing deduplication? What algorithm we're using? Things like that. Yeah. Okay. So here's some different domains. And then here's another one where they trained a model to detect whether pages are educational. And so here what they do is they use a language model, but they use it just to get labels. So they give the language model a page and they say, is this educational or not? And then again, since they want to run it on, you know, terabytes of data, they actually train this fast bag of words classifier using that data. So yeah, here they apply it to this like 15 trillion tokens data set, and they get this educational data, which is like 1 trillion tokens. And then again here, you could see that training on this kind of educational distribution, I guess, or data is having much better performance on this kind of reasoning benchmark versus just training on the still high quality, but kind of just general web data. So then, as I mentioned in practice, the training data will be a mixture of different parts. So here's the one from this Olmo 2. This is from AI2. And you could see that here they have open web math, but it's just 12 billion tokens out of almost 4 trillion. So most of the large proportion of data is coming from web pages in their mixture, and then they add in these other things. Okay, so I think we're gonna get kind of low on time for the last section. But here is the recap of the data considerations. And then if you look at recent examples, yeah, as I mentioned, the size keeps increasing. You have these different mixtures, and then the domain-specific ones will be usually smaller, or definitely smaller. Okay, and then we're probably going to run out of time on this, but let me at least start this, and then I could decide if we include it in a later lecture or just what we'll do, because these are some kind of interesting ideas. So here we saw that, yeah, as we increase the size of the model and have more data, then we can get a better loss. So a kind of unified way for thinking about this is we want to have some compute, and then we want to ideally just like use more compute to get a better model. So there's this idea called the bitter lesson, and it says that the kind of biggest lesson from the past is that general methods that leverage computation are ultimately the most effective and by a large margin. And so ideally, we want some way of just saying, okay, I'm going to like spend more compute on pre-training, and the model is going to get better. Well, then you have to think about like what is computation and what is compute, and how should I kind of spend it? Well, what compute means is actually doing these like forward passes and backward passes on different training sequences. And what you could do is you could actually like calculate how much compute in terms of floating point operations, like how many operations are being performed when you do a forward pass and when you do a backward pass. And then you could say like, okay, given that my model is training on this much data, here's the total amount of compute used during pre-training. Now, if you work this out in detail, then it's maybe some like long formula. So in practice, people will use these different approximations. So this is a kind of widely used approximation, which is just 6 times the number of parameters in the model times the number of tokens that you're training on. And that is the total amount of floating point operations used by pre-training on that or training on that data set. So for example, to pre-train Llama 2, you use like this 10 to the 22 flops. So then you could say like, okay, if we want to increase compute, then there's basically two different decisions. One is we can increase the number of parameters, and the other is we can increase the number of training tokens. And it turns out that doing this kind of choosing whether you increase the size of the model or the number of tokens can lead to different changes in performance. So there's this idea called scaling laws, and this will try to look for different relationships between especially compute and some other quantity. Maybe this is written a bit flipped. And what this is showing is they're basically training models of many different sizes and many different numbers of tokens. And then you could say like, okay, each one of these blue lines is a model that they're training. And at any given point, they've trained a model of a given size on some number of tokens. So that is some amount of compute. And what this is showing is that at any given amount of compute, there's actually some optimal setting of the model size and the model size and the number of tokens. And that'll be called the kind of compute optimal configuration. So then like what this scaling law is showing is that if you allocate compute optimally, then if you just like increase the budget and allocate it optimally, then you get this like predictable decrease in the test loss. So anyways, that's the kind of famous scaling law, and you can actually come up with a formula for it. And you can use these scaling laws for different things, even for like picking hyperparameters or choosing like the optimal model size for a given level of compute. So we're almost at the end, but maybe I'll try to incorporate these last slides into maybe the lecture on scaling later in the course. But we actually got through most of the content. So hopefully that gives you a nice overview of pre-training.